Concentration calculations. So concentrations is a quantitative, so a value, a measurement expression that relates the amount of solute to the amount of solution. So there's three different types of concentrations we're going to look at. So the regular household products, the stuff that you can buy in the grocery store or at the drugstore. Chemistry, molar concentration. So this is what I usually deal with as a chemistry teacher or somebody working in a lab would deal with. And then we have environmental concentrations such as parts per million or parts per billion. Anybody working in the environmental field or an analytical chemist would be using these values. So household products. Whether you purchase hydrogen peroxide at the drugstore or sour cream in the grocery store, the concentrations are stated as a percent. Like here, sour cream, 14% milk fats, 3% topical solution, so 3% hydrogen peroxide, the rest is water. And then 5% acidity, so 5% acetic acid, and the rest is water. So these percent concentrations can be reported three different ways: percent by volume, volume over volume, percent weight by volume, weight over volume, and percent weight by weight, weight over weight. So the concentration is represented by a small c, and it's the quantity of solute over the quantity of solution times 100%. The units that we use in this type of concentration are always going to be grams or milliliters. So if you have your mass in or volume in any other measurement, you have to convert to grams or milliliters when using household concentrations. So what is the weight by weight concentration of 40 grams of sodium hydroxide in 400 milliliters of water? So this is present in the smallest amount. This is present in the greatest amount. So sodium hydroxide is our solute. And then 400 milliliters of water. We want weight by weight, so these have to be both in grams. The density of water is 1 gram per 1 milliliter. So 400 milliliters times the density of water is 400 grams. So show this conversion or have a statement when you do your calculations, because you can't just change the units in a question. You actually have to state why it changed. All right, so C, and this is weight per weight, is equal to the mass of solute over the mass of the solution times 100%. So we're going to take 40 grams. We're going to divide it by 400 grams times 100%. So this is equal to 10%. So the weight by weight concentration is 10% for sodium hydroxide in a water solution. So in an aqueous solution rather. So 10%. How much acetic acid is dissolved in water if it is 2.5 liter of a 5% vinegar solution? So we have 2.5 liters. That needs to be in milliliters, so multiply 2.5 liters. This is the conversion factor. There's 1,000 milliliters in a liter. So either make a statement about the conversion or show the conversion. All right, so concentration is the volume of our solute over the volume of our solution times 100%. So we want to know how much is dissolved in water. So we're looking for the volume of solute. So if we rearrange this equation, the concentration times the volume of our solution divided by 100% will give us the volume of our solute. So 5.0% times 2,500 milliliters divided by 100% equals 125 milliliters. So 125 milliliters of acetic acid is dissolved in enough water to make 2.5 liters, and that will give us a 5% vinegar solution. Molar concentration. So this is the most important concentration for a chemist. And molar concentration is the moles of the solute divided by the volume of the solution. This time, the C is a large C. It's a capital C. So it's moles over liters. In university, you might have a professor that talks about molarity. Which is given the symbol big M, and that is the same thing. It's moles per liter. We now call it molar concentration, but he might say, or she might say, we've got a 2.5 molar solution. And what that means is 2.5 moles per liter. So, similar concept, except they use big M instead of C, and 2.5 molar means 2.5 moles per liter. What is the concentration of a solution that contains 16 grams of sodium chloride, so NaCl, in 200 milliliter solution? So we want moles per liter. So we're looking for big C, which means we must know N and V. Well, we know volume, and we don't know moles, but we do have mass. So this is a two-step problem. We have to find the moles of sodium chloride and then divide it by the volume. Now, this type of concentration, your volume has to be in liters. So we also have to convert 200 milliliters to liters. So I'm going to do that first. So I'll show you using formulas, and I'll show you how to do this using dimensional analysis as well. So this is 0.2, don't drop those zeros, 0.200 liters. And we've got 16 grams of sodium chloride. Okay, so we also have to calculate the molar mass. So show this step, don't just plug it in to the question like you could have looked it up on the internet. So the molar mass is 58.43 grams per mole. So first we need to find moles. So we take the mass and we divide by the molar mass. Because we are using the formula, N is mass divided by molar mass. So this will give us the number of moles, and we're going to keep more than 3 significant digits because this is an intermediate calculation. So we're using this number again. So that gives us the number of moles. Now concentration is moles divided by volume. So 0.27383 moles divided by 0.2 liters. So the concentration of this solution is 1.369 mole per liter. We can have 3 significant digits in our answer, so 1.37 mole per liter. Now, if you're going to do dimensional analysis, we know that our final answer has to have moles per liter in it. So we want moles per liter. So we're going to look at some pieces of information in order to get those units. And you would set it up the same way. You would calculate your molar mass, you've got your volume, you've got your mass, you've got your conversion factor. So you can either convert it and just use the volume in liters, or you can actually include the milliliters and the conversion as part of your dimensional analysis. I'm going to do just using the converted already. So we need from these 4 pieces of information moles, and we need it on top. So we're going to use the molar mass. So 1 mole contains 58.43 grams. Now we want to get rid of the grams, so we need the 16.0 grams. So now we have moles, but we need to introduce liters. So liters has to be on the bottom, so you take your 0.2 liters and invert it. That's 0.200 over 1, so it becomes 1 over 0.200 liters. And that way, we have liters and moles in our answer. So 16 grams divided by 58.43 and divided again by 0.2. If you were going to include the milliliters, then you would have one extra step. I will do it in red. So 1 mole over 58.43 grams, because that would give us the moles on top. The 16 grams gets rid of the grams. Now I need liters on the bottom. So I know 1 liter contains 1,000 milliliters. So this gives me liters on the bottom, but I have to get rid of milliliters. Milliliters on top, so milliliters has to be on the bottom in our last step. So now milliliters cancel. So this time I would take 16 times 1,000 divided by 58.43 and divided by 200. Another typical question, what is the number of moles? So we're looking for N, needed to make 200 milliliters of a solution with a concentration of 0.1 mole per liter. So in this case, we need to find the number of moles. So we know C is equal to N over V. So N is C times V. So we take our concentration, multiply it by our volume, which is 0.2. Liters cancel, and we have moles. So 0.02 moles, because I need two significant digits. Now, normally we wouldn't be measuring moles in the lab, we'd be measuring mass. So if it asks for the mass, you find the moles first, then you take the moles and you multiply it by the molar mass to get grams. And grams is something you can measure in a lab. Environmental concentrations. So these are a special case of the weight per weight concentrations. So you may have heard of them in the news. Environmentalists keep track of very low concentrations. So parts per million. Parts per million is 1 part per million. And then parts per billion is 1 part per billion. There are even parts per trillion. So these are simply ratios. Parts per million is equal to milligrams per liter, or milligram per kilogram, or microgram. A microgram is equal to 1 times 10 to the negative 6 grams. So, or it's equal to microgram per gram. So what normally we do is we take the parts per million, and the first step is to convert it to milligrams per liter or milligram per kilogram, depending on what the question is asking for. All right. A 250 milliliter sample of water contains 2.2 milligrams of oxygen. What's the concentration of oxygen in parts per million? So we're going to use the milligram per liter for our ppm. So if we multiply this by 1,000 milliliters under 1 liter, then we have 0.25 liters. So we have now our volume and our mass. So 2.2 milligrams divided by 0.250 liters. So in your calculator, 2.2 divided by 0.250. So this is equal to 0.80 milligram per liter. And milligram per liter is another way of writing ppm. So 0.80 ppm. If we multiply this number by 1,000, we would have parts per billion. So if you multiply that by 1,000, that would be equal to 800 parts per billion. There's a 1,000-fold difference between parts per million and parts per billion. This is the answer we were looking for. How much dissolved oxygen is there in 4 liters of water if it contains 300 parts per million oxygen? So we want to know how much dissolved oxygen there is. We know the sample size is 4 liters. We know that it's 300 parts per million. So 300 ppm can be written as 300 milligrams per 1 liter. So milligrams per liter. All we do is we change ppm to mg over L. We could have done mg over a kilogram if we were given a mass instead of volume for water. So we know that it's 300 milligrams per liter, and that's milligrams of oxygen. And we know we have 4 liters. So if we multiply this by 4 liters, our liters cancel, and we know that we have 1,200 milligrams of oxygen dissolved in 4 liters. So it's pure algebra once you change the units. So just to recap, concentration, we have weight, we have household products, which are weight per weight, weight per volume, or volume per volume, and those are given as percentages. Small c, milligrams, grams and milliliters are units, and then molar concentrations, moles per liter. This is more used if you're in a science field. And then parts per million, change the units. And that's mostly used in the environmental field.